guys watch? How's the project going on? Is everything okay so far? Are you guys stuck?
Oh, we sent some questions to you.
I'm sorry, I was down this weekend.
It's on the dimension.
The dimensions, you guys want to check your models?
Yes.
It's the right one? You did?
National.
Did you watch the videos when I were explaining like every parameters, or you guys want to double check?
Just double checking.
Okay, maybe after the class, if you guys have time, if you want to check with me, it's fine. I'm sorry this weekend was busy with a lot of stuff, but okay, so that's for the project. I guess by the end of this month or in, I think that the last week of classes is the first week of December. Okay, so we have like 1 month from now. So I believe in this week, we're gonna have 2 lectures, Tuesday and Thursday. Tuesday is gonna be the second midterm, and Thursday is gonna be the project presentation. Okay, so we have 1 month. This 1 month, we were supposed to finish some content related to structure analysis, and we are gonna have a midterm on this content. We're gonna have like around 7-8 lectures to cover this part, and during this month, you will have to work on the course project, and I guess you guys have the template, the Word file. So this is how the final project is going to be graded. So there's 3 parts of this project. The first part is the report. The second part is the presentation. The third part is the final documents and models that you're going to send to me. But the biggest part is on the presentation and the report. What I'm looking for in the presentation and report is that you present to me your final results, like how was the interstory drift look like for all the models that you have, and maybe you plot one curve that shows me how was each parameter, the interstory drift, the total drift, the shear lag, all these information needs to be presented for each model and for the comprehensive analysis. Okay. All right. Have you guys got a chance on Tuesday to watch the video on this? Is everything okay, or?
I couldn't really see the.
All right. I'm gonna go through it very quick because that's really basic stuff that we need to build on. So, if you guys remember, I know it was a long time ago, but we started a structure analysis of structures deformation based on analytical methods. These methods includes double integration method, conjugate beam. What else? Did we try any other methods?
There's 2 methods.
Yeah, okay. Double integration and conjugate beam. So there's other methods for deformations or structure analysis of structures. These methods include work energy methods, that we use the concept of work and energy to find the deformation of structure, and some other methods is called flexibility methods. So in 2 lectures, we are gonna cover the work energy methods, and then we are gonna start the flexibility methods next week. Okay, so let's so for work energy methods, right here, work energy. So for work energy methods, we use the concept of, like, if you have a beam or something and you put a load on this beam, this load is making an external work, and external work is something like, you guys know the work concept. Like if you have a body and this body is like this, and you put a force on this body, the work is external thing, not internal. Okay, so this load is B, and this body moved distance x. So the work done on this body that allows it to move is the force multiplied by the displacement of this body, B multiplied by x, right? All right, but it's not like the direct multiplication. It has a rule. Like, let's say, for example, I'm trying to push this thing, but it didn't move, and let's say it moved that way. So the work done by this force on this body is 0 because it didn't allow a displacement in the direction of force. So it moved that way maybe because another force was much bigger, move it that way. So this force make work 0, but other force make work. So the displacement need to be in the direction of work, okay? All right, so the actual rule is work is the F dot product, actually it's the vector of the force, dot product of the displacement x. And dot product mean is like, it's include the cosine of the angle between the two systems, okay? So, and work is a scalar quantity, not a vector quantity. Like we cannot say it's a work in the x direction or it's in a work in a y direction. It's a scalar quantity, the total amount of work that this body is doing. So the dot product of two vector quantities, as you guys remember from basics, it's a scalar quantity and it's equal to the magnitude of the vector f multiplied by the magnitude of the vector x multiplied by cosine theta, the angle between them. Well, let's say that this is x and this is the force f. This how's the vector look like? That's the direction of this vector and the direction of this vector. So, and this is the angle between the two vectors, theta. So if you want to find out the dot product between these two, you get the magnitude of f and the magnitude of x and multiply by the cosine theta between them. And that's actually explaining here. If this force is pushing this body in this direction, so the angle between them is 0, right? So cosine 0 is 1, so that means it's the direct multiplication of p by x. Is that right? Okay. But if there's an angle between them and this angle is 45 degrees, so that means only one component of this force is pushing this body in the x direction, and this component actually is the f cosine 45. So f cosine 45 is going to be multiplied by x, but the f sine 45 has nothing to do with the displacement in x direction. It's impossible that a force in the y direction can be responsible of a distance in x direction, okay? So that's why f cosine 45 multiplied by x is gonna give you the work in that move that body in the x direction, which explains this rule. You basically multiply f by x cosine the 45 degree, okay? All right, so actually that's the concept of work, all right? Same thing, if you have a beam, like let's say that we have a beam like this, like a cantilever, and this cantilever has a load B, and this load B make this cantilever move a distance delta. If you want to find out the work done by this force B on this beam, you multiply B by delta. So that's the external work done on this beam. This external work was converted into a strain energy inside the beam. Like let's say that this beam is like this, and you put a force, and this force made the beam goes down, right? So it put a work on this beam. So the work that you have done on this beam was transferred in a form of energy inside this beam. Once you remove the load, this beam is gonna go back to its original position. And this strain energy is coming from the bending moment on this beam and the shear on this beam, and all the internal forces happened inside the beam. So the concept that we have here is saying that the external work exerted on a structural system is equal to the strain energy is stored inside the system. This is external work. And this is strain energy. All right, so as we said here, that W is gonna be the force multiplied by displacement, right? But they both need to be in the same direction. Right now we didn't talk about the strain energy much. We just like say that it's going to be stored inside the body. But what we want to do right now, we want to find how we can calculate external work on a structural system, not rigid bodies. Okay, our structures is not like this. It's not something that is moving. Okay, but I'm just giving you an example how's the work is, and we need to find out how's the strain energy is stored inside, because here's a different concept. I teach you this in engineering dynamics for undergrad students. Here, the work that you put in the body was converted into dynamic movement in this body. But right now, the work that we put on our structures is converted into strain energy inside our structures, because our structures is not dynamic, it's not a mechanism. Okay, so we need to figure out these. So our structures is kind of different from these. Like when you put a load on a structure like this, delta doesn't happen right away. Have a linear relationship. Like when you increase B, delta is gonna get increased. Okay, so that's what happens. So there's a linear relationship, and actually for this rule to be applied, we are dealing with linearly elastic materials. If the material is not linearly elastic, this thing might not apply. We need some modification because some strain energy was converted into cracks or into other things. We need to be in the linear elastic phase. And for the linear elastically material, we can apply Hooke's law that there is a linear relationship between B and delta, and we all know what is the factor of this linear relationship, B equal K by delta. So it's a linear relationship. So the relationship is something like this. If you have like the force, like let's say that we have B, and we are gonna say this is delta. B and delta are gonna be, we're gonna use them to express external work, okay? We're gonna use P to express not Bx. We're gonna use P and this delta, right? And if we have the external work as a moment, like you put a moment on your structure, so we are gonna have M and theta. So for linearly elastic structure, usually the relationship is line, something like this. And if you wanna find the work is the area under this curve, something like this. So it is usually, because this rule, the one that I put here for work, it is usually something like this, the integration of F dot product of X. Because sometimes the forces keep it changing and sometimes the X is changing. So if you wanna actually capture the relationship, if both of them are constant, so that can be applied. But if they are changing, you need to apply this over the length of L of your beam, dx. That's actually how's the rule. And if we want to apply the same rule here, if you want to find the work is going to be the integration of B multiplied by delta, and this is going to be, and actually you can put cosine theta, but we are assuming that B and delta are in the same direction. And then you are gonna, even if you wanna find the work, this is work done by B, let's put the work done by the moment, same thing, the integration here from 0 to the final delta, and here's the integration of M theta, and then you are gonna put here from 0 until the final theta. So if you wanna integrate B with delta, and you have the curve between them, I'm not sure if you guys know this rule, it's the area under the curve. And that makes sense. Why? Because let's say that you have the relationship B equal, I don't know, like let's say K multiplied by delta. Once you integrated this, is gonna be like, once you capture this, it's gonna be line. If you integrate it, it's gonna be the area under the curve. So we can actually say that this is equal to B delta over 2, same thing here, M theta over 2, like something like this. So that's actually how work on our structure look like, all right? But let's say, what if we have a function? If we have a function, we can do this. Like, let's say that the relationship is something like this. We can take the area under the curve, like say that the work done by B on the structure is the area under the curve. We have to integrate. Like we have to know what is the function. Let's say that the B is equal to, for example, let's say ax squared plus bx plus c. So you need to integrate this, ax squared plus bx plus c. So once you integrate, this is gonna be cubed, this is gonna be x squared, and then you are gonna do all the integration. But, or our application is something like this, not like this. So this applies, b delta over 2 over m theta. All right, okay, so that's for the external work. How about, let's talk about the strain energy. Strain. Okay, for strain energy, let's talk about strain energy stored inside bars. Bar means like truss member. Because strain energy, it's all about what is internal force inside our structure. If your structure has only normal force, that's very easy. But if your structure has bending moment, shear, and normal, so the strain energy comes from all the internal forces inside your structure. So bars are the most easiest things to deal with. Why? Because they only have one internal force, which is the external B. So B is an external force that is going to exert work at our structure at this point and make it maybe elongate. Like, let's say that our bar is going to be something like this. Once you do it. And it's going to have delta. Okay? So delta, we are going to use it for the internal deformation. But this delta, we are going to use it for the external movement. Okay? So delta is the internal deformation inside our body. And let's say that this is delta L. All right? And if you have B outside, there is an internal tension inside your bar. We are going to call it F. So we are going to use B as an external force, and we are going to use F as an internal force. Okay? So that's B is external, F is internal. All right, so you have F and delta L. Same thing, same rule that we have here is going to apply for bars. You apply your B, and delta is getting increased linearly, same thing. F is going to increase linearly with the internal deformation. So the internal strain, or the strain energy inside, is going to be half F multiplied by delta L, right? Same thing, that's for bars. So the work and the strain energy. But we know interesting rule about the deformation inside our structural member. Do you guys remember the stress-strain relation? That epsilon is equal to sigma over the area of the cross-section, right? Sorry, actually, E, Young's model is sigma over the strain, right? Or epsilon is sigma over E. All right, like we can write it sigma over E. All right, so epsilon is equal to delta L over L, right? The deformation inside our structure over the length of the beam. Okay, this thing. So we can say, and actually sigma is equal to the force inside over A, and this is E. So we can say delta L over L is equal to F over A, and we have E here. So we will end up with the delta L is equal to F L over E A. This is it. So we can apply this here, that the strain energy is equal to half F square L over E A. All right? So right now we can say, we can put a rule here from the external work equal to the internal strain energy is gonna be half B delta. B is an external force, delta is external displacement, is equal to half F squared. F squared is the internal force inside the truss member or inside the bar member, square L over EA. And that's actually what we call it, the real work equation. All right? because we are gonna have something that's called virtual work. So this is called real work. All right, or the stresses or the work energy equation, all right? So let's see how we can apply this, but before we do this, let's go to because I explained how we get the strain energy in bars. Let's do the same thing, number 3, in beams. Same concept. All right, in beams is a little bit complex. Why? Bars only have normal force, so you only have one force. But in beams, you might have normal, shear, and bending moment. However, bending moment is the responsible of over 95% of the deformation. Shear contribution to the amount of deformation that happens to the beam members is very low amount. That's why sometimes we neglect it from our analysis. However, if you look in the textbook, they always show you how you calculate the shear deformation, the torsional deformation, everything, and then they put an example, and the example calculate the deformation from all the internal forces, and you will find out that the moment has like a deformation of, let's say, 6 millimeter. And the deformation that comes from the shear is 0.001 millimeter, and the deformation that comes from the normal force is 0.002 millimeter. So it's not worth it to spend a lot of time on calculation to a number that is gonna be rounded, is not gonna show up in the analysis. That's why most of the focus in the deformation analysis is based on the bending moment or the rotation. Okay, so right now we are gonna focus on the deformation that comes from bending moment. So let's say that we have a beam. Put this here so you guys can see. A beam like this. And this beam has a load, like let's say normal, like any load, like distributed load, whatever loads that we have, and then there's gonna be deformation here. And we need to find the value of this deformation. So if I took a section in this beam out, this section is gonna look like something like this. All right, what happens in this section when it's bending happen? When bending happen, when it's gonna happen something like this, it's gonna have tension down, and we are gonna have theta here, and here's like tension, up there is compression. This is due to the bending moment, and that's what we are looking for, the strain energy that comes from the bending moment. And it has a similar rule like here, half F multiplied by delta L, same thing, the strain energy in beams is half M multiplied by theta. But the thing is, it's not like here, like delta here is constant, but here, over the length of the beam, every point has completely different theta. Theta is keep changing with X. Like here, there is a theta. Here, there is a theta. So it's not like here that the delta is constant. So basically, we can't write it that way. So we need to write it in a different way. So if we have something is changing, we go back to the derivative. Like we can't deal with the entire structure that everything is uniform. So we come here and take a section, and this section, we can generalize a rule on this section. Like we can say that the infinitesimal strain energy is stored in this bar is equal to half the amount of moment here multiplied by the d theta here at this part. Do you guys understand that? That's how we do it. All right, so du is equal half md theta. And we know a very, very important rule that we proved before. Do you guys remember what is y double dash equal to? M over EI. You guys remember this? We proved that a long time ago and we always use it. If you guys remember this, this is equal to d theta dx, right? Because we have y and we have y dash, which was d theta dy dx, which is theta. If we differentiate it another time, it's gonna give you y bar. So we can say that d theta is equal to M over EI dx, and then we come back here, have M multiplied by M over EI, and this all multiplied by dx. So du, the infinitesimal stored strain energy at this location is equal to half M squared dx over EI, right? Still, this is only the strain energy in just a small part of the beam. Why did I take this a small part? Because I know this is an infinitesimal area or an infinitesimal section, and the strain energy stored is not, it didn't get a chance to change. That's why we are talking derivatives and integration. So derivatives, because we are talking about a small thing. If we want to capture this at the entire beam, we have to integrate this equation. How? M is going to be not constant. You are going to substitute with the equation of M over the entire beam. Then you integrate this over the entire beam, you can get U is going to be the integration from x equals 0 up to x equal L, and this is going to be half M squared dx over EI. And this is going to be the strain energy stored inside the beam. Do you guys have any questions?
Yeah. The value of M is the maximum moment or the moment?
No, it's going to be the equation of moment, not the maximum of moment.
Okay.
Because the moment is keep it changing. The strain energy stored here is a small, like get bigger until it gets to the maximum, so all the particles of, there's energy stored in all the beam, but some of them has a high energy, like the one that has maximum displacement, and one has a low energy, but the total energy is all the particles that have the that have a strain energy. So that's why we did integration. Okay, that's actually how the concept of integration is important, because of non-uniform things. Like when there's something is not uniform, we take a small thing, and once we take it, we deal at the derivative level, and then if we want to take it for the entire structure, we integrate and using the function that describe the things that is variable. And the only variable that we have here is the M and theta. And we moved theta, that's actually what we were doing here. We tried to, rather than having d theta, we convert it to dx. So you either get the function of d theta, like find how it's varying, but it's better for me to get the equation of the bending moment and make it as a function of M and x, rather than having as a function of theta, all right? So that's why I use the relationship between d theta and x and moment and get an equation here, M over EI dx. And right now, if I know the equation of the bending moment as a function of x, I can solve this integration, all right? Okay, so let's see how we can apply this. But before I do that, when I did this thing, I did it only on one bar, right? Okay, but let's say if I have a truss like this, and I have a hinge, I have roller, and then I put like a force here, and this force is equal B, and this point is gonna move delta. So the external work done on this truss is B multiplied by delta over 2, right? Because it's based over this, right? We know that part. But all these bars are gonna have tension compression, right? So the work done on this truss is converted to strain energy in all the truss members. So if you wanna find out the total strain energy stored inside this truss, you need to find the forces in all these trusses, okay? And then you apply this rule. The force in truss member number 1 is squared multiplied by the length of the truss member over EA. And member number 2, 3, 4, all the truss members, okay? I'm gonna solve an example that has only 2 members so that we don't spend a lot of time, but if you have a big truss that has 100 members, you have to do it for 100 members. This one I'm not gonna give it in homework or anything, but that's how the concept is. We usually do it in a table. Like we usually have a table like this, and I put in table number 1, like the force, the length, the E, the A, and then at the end, I calculate half F squared L over EA. Like say that's truss member number 2, 3, 4, 5, and then I put the force in member 1, the length of member 1, the E of member 1, and the A of member 1, which is usually the same of all the members. Sometimes cross sections are much bigger, so they have different area, but if they all have the same material, so E is constant, and at the end I multiply half F squared L over EA and get all of them here, and at the end I get the sum of this, and once I get the sum of this, I calculated this part. So the general rule of this is something like this. Half B delta, which is the external work, is equal to the sum of half F squared I multiplied by Li over EI AI from I equal to 1 to I equal to N, which is the number of truss members. Okay, so that's the general rule. Okay, so let's how this can be applied on an example. Okay. Right, so this example is saying using the method of real work, okay? This is called the real work because we're gonna take another method, it's called the virtual work. Using the method of real work, determine delta x. Okay. I have this truss, this is 15 feet, and this is 20 feet. And I'm saying ABC, and we have a load here. kips. And I'm asking about what is the displacement delta x here. That's the question. And I give you information that the area of all cross section A is 2.4 inches squared, and the Young's modulus is 30,000 kips per square inch. Kilopound per square inch. Okay, so that's the givens. Let's get the solution. We only have one rule in the method of real work. What is this rule? It's over there. That half B delta x is gonna be equal to the summation of half F squared L over EA. So I know B, it's a 30 kips. I don't know delta x, that's the one that we are looking for. I don't know the forces in the truss member, but I know all the lenses, all the E's, all the A's. So I have only one thing to find, which is the force in the truss member. So it's like a simple truss that we want to solve. So basically, actually, like when you push this by 30 kips, this point is gonna move that way, and this truss is gonna be something like this. And maybe this point can move, like it cannot, maybe something like this. So that's what is gonna happen to the truss. And because of this, there will be some strain energy stored in this truss, and that's what we're trying to figure out here. So to solve this, first I need to solve this truss. How? You have a truss, a determinant truss has 30 kips. So first thing that you wanna solve is that you get the reactions. So let's get the reactions. All right, what is the X reaction here? 30, right? Because you have a 30 here and there's only X, sum of X is equal to 0. So you are gonna have this as 30 kips. By the way, you have to solve this using the basics of structure analysis, not like you say sum of the X and then the Fx or the Cx is gonna be 30 kips. And then you need to find what is the reactions here.
Some of the moments.
So from my perspective, what you are gonna do, you get the moment at this point so that you are gonna get how much Y reaction you are gonna hit, and then get the moment here, and you are gonna find the reaction here. But there is like a shortcut to this. Like if I wanna make sure that what I did is right, I know that 30 kips is gonna make a moment of 30 multiplied by 20, which is gonna be 600 kip speed, and it's gonna rotate the stress that way. And I need a counter force between these two reactions that can induce this moment. So if I divide 600 over 15, it's gonna give me the amount of reactions here. So this is gonna be equal to 40 kips and 40 kips. Try to solve it using structure analysis, it's gonna give you the same thing. You need these two to counter the moment that comes from the 30 multiplied by 20. But you need to solve it using structure analysis. I solve it, I got the reactions. Next thing, I need to find the forces inside the truss member. To find the forces in the truss member, you guys solved the trusses before. You cut at each joint and then do sum of Fx, sum of Fy at each separate joint. Same thing here, you have two members, so you are gonna find out the force in this member and the force in this member. But actually, it's very easy for me to find these two members. Why? Because if I did sum of Fy at this joint, I will find out that I have compression here of 40 kips. Why? Because I have 40 and I need 40 here. And if I want to find the forces here, it's going to be 30 kips here, because I only have this force and this member is not inclined. It's vertical and horizontal. So it's going to be negative 30 and negative 40, because we're going to have the compression as a negative and the tension as positive. But does it gonna matter if a member has a positive or negative when it comes to energy? Like there's no negative energy, right? Okay, why? Because at the end, all of them are gonna be square. So that's why it doesn't gonna matter. But let's keep it that way, because we're gonna have a virtual work method and we're gonna see how this is gonna make difference. And then once you knew the strain, the internal force in this, you can also solve this to get the internal force here, and you will find out. Do you guys know how to solve trusses? Absolutely, right? Basic structure analysis. You cut at this section, and then you are gonna have F here. Like if I wanna solve this, it's gonna be something like this and this. Here's the force. The force here is 30, and this is I don't know, like F, and I have a reaction here. So you are gonna have here F sine theta, and here F cosine theta. And then you take sum of in the y direction, so like here is 40, so 40 is gonna be equal to F sine theta. Try to find theta from the dimension, then you are gonna find what is the F equal to, right? Okay, so once you solve this, you will find that this member has positive 50, and that makes sense that it's positive. It's gonna be tension because this is the member that is gonna be pulled away. So I got the forces in all the members. Right now, I'm ready to solve using this rule, but be careful. Why? Because some of the things that I have are in inches squared and the lenses are in feet, okay? So let's pay attention. Okay, so I have half multiplied by the B, the external force, which is 30, multiplied by delta X, which I don't know, equal to, let's see. Since they all have, EA is constant, so I'm gonna put E 30,000 multiplied by 2.4. E and A are all in inches squared. And I'm gonna put half down there, like let's put 2 here. Up there, I have F squared multiplied by L. Let's take the first member. So I'm gonna have 30 squared multiplied by L, which is 15, plus 40 squared multiplied by 20, plus 50 squared multiplied by, the length, you guys take the square root of 15 and 20, you'll find that the length is 25. Am I missing something? I multiplied F by every L.
Inches.
The inches, right? I need to convert all these 15, 20, and 25 from feet to inches. So you need to multiply all this by 12. I take 12 as a common factor. So once you do this, you can actually write it 30 squared multiplied by 15 by 12, 40 squared multiplied by 20 by 12. Or you can put it as a common factor, and then at the end you will find that delta x is equal to 0.6 inch. All right, so you guys tell me, is that simple or difficult? Only one rule, this rule. You know structure analysis, you can apply this to any truss. You solve the truss, get the force in every member, and then once you get the force in every member, you will be able to solve this, okay? All right. So this is gonna take us to a new concept, which is the virtual work. Sure if I should put this. It's gonna be so close. Not a good idea. Does anybody have any question till now? All right. It's boring, right? ETABS 2000 is much better. Huh? Yeah. I know. Is it boring, really?
No.
It's good, right? Okay. Well, I enjoyed software too. Like when I was undergrad, I really liked software. But understanding the basics is very important. Like when you know the science behind everything. Like to be honest, when I got taught this stuff, my professor never go through all these things. We always get back to this rule that this one? Like the force multiplied by delta is equal this. This is the internal, this is the external. But I had to do my work on my own to figure out where this is coming from. And I thought, maybe you guys, if you know, it's much better to know where everything is coming from. But at the end, I'm not doing this to complicate things for you. What do you need at the end? Maybe I will not ask you where everything's coming from. All what you know is to know how to use this. Because it doesn't make sense that you understand everything where it's coming from, and then when it comes to substituting in the final rule, you mess it up. Okay? So, what I need from all that, I don't need anything from all that. I only need you to understand this. What is this? What is that? What is this? What is that? Only one rule. Let's say, oh, I didn't understand any of these. Maybe you need to dig and do your research and know where is this coming from. But at the end of the day, you know how to use this rule. This external force, external displacement, internal forces. That's it. Very, very simple rule. However, when I apply this, these rules are stuck in my head because this is the only thing that they explain in the lecture. So this thing needs to be stuck in your head. Work, energy, how to calculate them, it's only this rule. Okay, all right, so let's get to the concept of virtual work. Virtual work is a little bit difficult, but we have to study it anyway because many concepts are based on virtual work. Like the virtual work itself is being used in the flexibility methods and methods of consistent redundance. Lots of methods are based on the virtual work method. And so let's, virtual work. Okay, so what is the concept of virtual work? All right, let's say that you have, okay, let me do it that way. I'm gonna do it in like the way that has been done back in the days when I was studying these things. Like when I was studying these things, all right, so if we have a structure, we have something called the summation of Q multiplied by delta B is equal to the summation of FQ, FB, L over EA. And actually, my days, this is what's called F1 and F2, not FQ. Q is related to something virtual, and B is related to the real structure. That's how I remember it. Like, it was something like that. And Q is always equal to 1. So it's always, that's how I remember, like, if I want to solve a structure, I remember this rule. I never forget it in my life. Maybe I forgot lots of these things, and before I prepare to the lecture, I need like to look like on all the rules and how to connect everything. But what I forget in my entire career, and I never forget it, this. Like, if I want to find delta is the integration of N1 into DL over EA. That's never forget in my life. And if I want a delta from the moment, it's going to be M1, M2, DL over EI. That's rules stuck in my head, never forget it. And I never, at that time when I was like undergrad, I didn't know where it came from. I had to dig after I graduated where this came from. But because I applied this to many rules, I know where they came from. So these things, the final things, that's the things that need to stuck in your head, because this is how you solve problems. But I do a little bit work to know where this stuff coming from, because you are graduate students, you know, to know what are you doing. All right, so let's see how we came up with these rules. First, we have the concept of virtual work. So this concept is saying, like, if you have like a truss member, something like this, and this truss member has a roller here and maybe a hinge here. Can I draw it one more time? Like this. All right, we talked about that we have strain, energy, and work. Like, we have two things. We have W and we have strain energy. We need to find both to figure out what we are doing. All right, so let's say we have this truss member. This truss member we applied a force P on this truss member like this. This truss member is hinged here, so it's gonna make a movement, something like this. This delta is external delta. We call it delta B, something like this. And we're gonna have a reaction, let's say that this is point A. We have a reaction RA, something like that. So there will be internal displacement inside this member. Like this member, the actual length is like this, but once we put B, it gets bigger, right? So if we actually want to find out how much deformation that this member have, we can draw a perpendicular line here. That is, this distance is almost the same like this distance. And this one is the internal displacement, delta LB. All right? So this is an external displacement in the direction of the beam, and this is an internal deformation. All right? This is the internal deformation. So, and definitely there's a force inside this member, which is RA. All right, so if we want to draw the relationship between the force P and the displacement delta, and the relationship between the force F inside this member and the internal deformation delta L, is going to be something like this. So let's say that this is going to be maybe something like this, and this is going to be something like that. This is, we are going to call it work. Let's use the same things that I'm using here. B. And this one is going to be strain energy, because that's internal forces, UB. And from this concept, WB should be equal to this. But let's put the deformation here. The deformation that we have here is delta B, and the deformation that we have is delta LB. If we want to make this equivalent, so WB is equal to UB, that means that half B, delta B, is equal to half F delta LB. Is that okay? Right? That's what we did actually here. We made another system, we call it virtual system. This virtual system, we are gonna apply not B, we are gonna apply a small force Q, maybe smaller than B, like something like this. We name it Q, so a smaller displacement is gonna happen, like something like this. And we're gonna have the same thing, delta Q, and we are gonna have delta LQ. Say if I name it right, yeah, delta LQ and delta LB. All right, and here we are gonna have a reaction RQ. What is the difference? This is the real system, and this is the virtual system. Why it's virtual? Because this force has nothing to do with the actual force on the structure, right? Okay, so let's see, it's gonna be the same thing, like if we wanna draw the relationship between B and delta, and this is delta and F. Since the forces are smaller, so we're gonna have something maybe like this, and this one is gonna be Q, this is the amount of force, and this is gonna be delta, sorry, should be delta Q, and this one is gonna be delta LQ, and this one is gonna be FQ. Here, the force is gonna be FB, yeah, FB and B. So that we use the same symbols. And same thing, the work here under this curve, WQ, is gonna be equal to UQ. So we're gonna have half Q delta Q is equal to half FQ delta LQ. All right, so that's for these two systems. But what if we combine these two systems together? What if we have system, we applied our virtual work and then applied the actual force on the system, how it's gonna look like. So let's say our structure is something like this. And once we do this, our structure is gonna be pushed much bigger displacement, is gonna be something like this. So this is gonna be delta L, and this is gonna be our new delta. So you are gonna apply Q, and then you are gonna apply B, both forces. Let's see what is gonna happen, and definitely we are gonna have a reaction here, RA plus RB, sorry, and plus RQ. Okay, let's draw this and see what is gonna happen. Like, we are gonna have, by the way, this system is separate right now, and this system is separate. Nothing to do, like the virtual force has to do with the real system, and nothing in the real system has to do with the virtual system. The thing is, we need to come up with a rule that the virtual system can affect the real system or get in the rule. Why we are doing this? Sometimes we can't solve the real system, but we create a virtual system that we can solve to let us know what is the result for the real system. Why we are doing this is because it's more simple. You know, sometimes you say, oh, you have 100 ton on this beam. The thing is, the number 100 is big. Sometimes you say, oh, I'm gonna put 1 ton and see how is the final value is gonna look like. And once I find the reaction, I'll multiply it by 100. Sometimes we do that, right? So that's what we're doing here. Like, rather than solving a very complicated real system, we come up with a virtual system that is very easy and solve it and do some manipulation to find the value of the real system. So that's what I'm doing here, putting two loads, Q and B, is gonna come up with this. Like, let's put here, I have the external force and the external displacement, internal force and internal displacement. All right, let's see what happened. First, I applied Q, and then I put more forces and I got to B. Then internal forces, I have FQ, and then once I put B, I added on top of FQ, and then I got to, this is B plus Q, because here, this is only B. Same thing here, this is gonna be FB, and here is gonna be FB plus FQ. All right? So how about deformation-wise? Once you put Q in the system, you are gonna have delta Q. And once you increase it to B, you are gonna have delta B. Same thing here. You are gonna have delta LQ, and then you are gonna have delta LB. The work under these curves should be the same, right? But we proved a little bit that this should be equal to this, right? Because we did this here, these two triangles. And this small triangles is the one that they are here, all right? And since this system is applied by B and Q, this triangle should be equal to this triangle. Why? Because the work should be equal to the strain energy. That means that this small rectangular here should be equal to the small rectangular here, right? So what we are gonna learn from this, we are gonna learn that the Q, the virtual load, multiplied by the real displacement, delta L, delta B, is gonna be equal to the internal force in the virtual system multiplied by the actual deformation in the main system. Okay, focus. Q is something related to the virtual. B is something related to the real. So this is how we combine them together. The virtual load that we put in our structure multiplied by the actual displacement on the real structure is going to be equal to the internal force in the virtual structure multiplied by the internal displacement in the real structure. You know, it's something like, you know, like if you, let's say that you have a member like this and you put 100-ton load like this and you make a virtual system. And let's say you don't know the displacement here, X is equal to, you don't know. And you put a virtual load 1 ton on this and you know that this is gonna move, let's say 2 centimeters, all right? So you say, if I put 1 ton, this is gonna move 1 centimeter. So if I put 100 ton, how much this is gonna be? It's gonna be 100, the real, multiplied by the virtual displacement over the virtual load. So you can actually divide here over the virtual load to find the actual displacement. It's something like this. Do you guys understand? All right, so this is the final rule. And this is actually a very, very important rule. But the thing is, make sure that you understand, Q's are virtual, B's are real. Like here, the 100-ton and this displacement are the real, the 1 ton and the 2 centimeter is the virtual system that helped me to solve the main system. All right, so let's actually get delta B. This is my biggest problem. Delta B, delta, I don't know it. Like you'll tell me, okay, I put 1 ton. How did you find that this is 2 centimeters? From the first principle, the relationship between the stress strain. Like how? We just came up with, where is it? Here, delta L B real is gonna be equal to F L over EA. But this F is real, FB, not virtual, FQ. So you are gonna have that Q multiplied by delta B is equal to FQ multiplied by FB multiplied by L over EA. And usually, Q we put it as a 1 ton because it doesn't make sense that you have a very complicated structure and when you put a virtual load, you make it a very, very big load. You put a very, very small load so that you can be able to solve it. That's why when we put Q is equal to 1, delta B is gonna be equal to this entire formula. And that's actually what I learned when I was in undergrad. Like actually my professor was like, I have really, really great professors, I'm not like undermining, but the thing is there was no time to explain lots of basics and they just wanna do lots of stuff. So the delta was always to be F1, F2, DL over EA. Was the rule. F1 was the virtual, F2 was the real, DL over EA, which like at the end, like if it's a changing, but if it's not a changing, like trust member, it's gonna be L, okay? So that's a very, very important rule. That's the most important rule for today. So let's solve a problem on this. We have a hinge here and another hinge here, so that means it's indeterminate. And I have a load of 30 kips. And I said using virtual work compute the components of displacement FB. I give you A is 2 inches squared, and Young's modulus is 30,000 kips per inch squared. Okay, I said the components of displacement. What does it mean? That means the X component and Y component. 16 feet. All right. So the thing is, our rule only have one displacement. So if we want to solve our structure in the X component, we need to make our virtual load in the X component. If we want to solve in Y component, we make our virtual load in the Y component. You'll tell me, but this is 30 kips. It's gonna be only X component. No, it doesn't matter. When you push that way, this bar is gonna move that way and it's gonna come a little bit down. So there's a little bit of Y component. X component is gonna be bigger, but there's also Y component. Like when you push this, it's gonna be, this one is gonna rotate, so you're gonna have this bar coming maybe here. It's gonna be something like this. So this point is gonna be a little bit down than the other point. So let's see how we tackle these problems. To tackle these problems, we only have one rule for virtual work. What is this rule? That the Q, the virtual load, multiplied by the delta that we are looking for is gonna be equal to the summation of FQ, FB, multiplied by L over EA. That's the only rule that we have. All right, I told you we are gonna make Q always one. How we are gonna make Q? All right, so right now let's find delta X. To get delta X, I'm gonna take the entire structure. Okay, I mean, this is the steps. First, you write the rule. Second step, let's solve this structure first. Like that, let's make this as a second step. Solving this structure, you need to find the reactions on this structure. To find the reactions on this structure, you are gonna find out that let me ask you, what is the X component, what is the X reaction here?
That's a tough one.
Well, it's a tough, but you know, like if you think about it, that's a truss member. If there is an X reaction here, and there is no truss member that can balance this reaction, so this is unstable. So when you take some Fx, like if you take this out, like if I have a truss that only has a member here, there's only Y reaction here. But if you have a member here, that means that this one can take X reaction. So it'll tell me that this is hinged and only have Y reaction, yeah, it happens. If there is no an inclined member, like if there is no a truss member like this or a truss member like this to balance the X reaction, so definitely this one is only taking Y reaction, okay? All right, so I know that X here is 0, so this truss member can take all the X that we have here. It will tell me why. I'll tell you because this is an inclined member. The inclined member is going to have an X component and Y component. So the X component is going to balance this reaction, and the Y component is going to balance the Y reaction that we have here. So the 30 kips are all going to be gone here. But if I have like the other problem, I'm not sure where, yeah, like here, I can say the same. Because I have a member here. So this member can take X reaction, and actually took all the reaction. All right, so I have 30 kips, and I can do the same thing. I know that this 30 and this 30 are gonna make a moment that has an arm 16. So if you multiply, if you have a calculator, multiply 30 by 16, can you do that? 30 by 16.
486.
400 divide them over 12, 40.
Yeah.
So I'm gonna have a moment, this, 40, and 40. Oh no, it's the other way. Why did I do that? This is the external force is gonna make a moment that way. So I need, oh, yeah, think about it. So I need another one to counter. So this one is gonna make a moment. If you can't imagine, like you can draw it, this is gonna make a moment counterclockwise, and this is gonna make a moment clockwise. So these two are gonna balance the other moment. If you can't do that, and actually I recommend not do it, you just take the moment here and get the reaction here, and take the moment here and get the reaction. But we are doing it so that we can do it fast. All right, so I have 40, I have all the reactions. Right now I can solve and get the forces in the member. To solve the forces in the member, this member need to be under compression to balance this 40, and it's gonna have negative 40. If I wanna find the force in this member, I'm sure it's gonna be tension, so it's gonna be something like this. And you can get the X component and make it equal to 40, or the Y component and make it equal to 30. So you will find out that this has a positive 50. I get all the forces. That's step number one. Step number two, write the rule. Sorry, step number one, write the rule. Step number two, solve the truss under the original load. If you want me to put it here, solve the truss under original load, OL. Number two, solve the truss under virtual load. But before this step, I mean, like, you can put sub-step. You draw the structure without any load. Like, I have this structure without any load. Remove all the original loads. What are you looking for? Are you looking for delta X? Put 1 ton in the direction of delta X. Actually, we are dealing kips, we put 1 kips. Okay? 1 unit load of the problem. If it's ton, put 1 ton. If it's kips, put 1 kips. All right? So I removed all the original load and I put only the Q. That's what we did here. We have one that only has Q. And then solve the truss with the Q load. Like, when you put 1, actually it's like a small problem of this. Like, I'm gonna have this, what is the reaction here?
130.
I'm gonna have 1 here. How about the reaction here? 1 multiplied by 16 over 12. So it's gonna be 16 over 12. 1.
1.33.
It's gonna be 5 over 3, right? 4 over 3. 4 over 3 and 4 over 3. It's gonna be something like this. So I'm gonna have negative 4 over 3 force here, and I'm gonna have positive 5 over 3 here. I found the internal forces in the virtual structure. Now I can apply it here. So I can apply, what is the value of Q? Q is equal to 1. So I can put 1. I'm gonna have 1 here, multiplied by delta X, the one that I don't know, that's what I'm looking for, is gonna be equal to member by member. Let's do it member by member. I'm gonna have FQ multiplied, let's take this member. This member is gonna have FQ, let's do the positive first. Okay, let's do 5 over 3 multiplied by 50. All of them are positive. Multiplied by the length of this member. The length of this member is 20. And I'm gonna multiply it by 12 so that I can convert it. And then I'm gonna divide by the area 2, multiply it by 30,000. I get the first one, plus the second member. The second member have negative 40 and negative 4 over 3. So negative by negative is gonna be positive, but I'm gonna put them negative 40 let's put the virtual load first. -4/3 multiplied by -40 multiplied by the length 16 multiplied by 12/2 multiplied by 3000, and then I will get the value of delta x, and this is going to be equal to 0.5 inch. Let's say that you put the one in the other direction. It's fine if you put the one in the other, you can put it in any direction. But you will find out, because when you put the virtual load in a specific direction, that means that you are assuming that the final delta is going to be in the same direction of Q. But if you, once you do it in the other direction, you are going to find out that delta x is negative. That means it is in the opposite direction of the one of the load that you put, okay? So that's fine as well. But to be honest, I would actually try to use my sense to try to assume where's the delta is. Like, I know that there's circuits going that way, so I put the virtual load in the same direction. So we're gonna do the same thing with Y. Look at what I'm gonna do with Y. Y, I'm gonna do the same thing. Let's say delta Y. I'm gonna draw the structure without any load, all right? I'm gonna put hinge here and hinge here. And then I'm gonna put the virtual work in the direction of Fy. You can put Fy this direction, like you can make Q equal 1 kicks. But to be honest, it's gonna have lots of negatives, because you're gonna have, at the end you're gonna end up with negative. But I know that this structure is gonna go down, so maybe I put the 1 ton going down like this and see what is gonna happen. So once I do this and solve for the reaction, you will end up with like, this member is gonna be a 0 member, okay? Why is gonna be 0 member? Because this part, this truss member is gonna have an Fx component. And when you take the summation of Fx here, there is no external force in the x direction. So it's gonna be F sine theta equal to 0, so F is equal to 0. So this member is gonna be 0 member, and you're gonna end up with this member has a compression of -1, and you're gonna have a reaction here is 1, and the reaction here is gonna be 0. And this is gonna be a very, very simple problem. Like when you apply here, Q is equal to 1, multiplied by delta Y is gonna be equal to -1, multiplied by -40, multiplied by the length of the member 16, multiplied by 12/2, multiplied by 30,000, and then you will end up like solving this problem. So the final answer is gonna be 0.128 inches. Is that easy? All right, so basically what we have done today, we went to the concept of real work, virtual work. It's only one rule, this rule, that's it. Like I didn't do anything, any rocket science, just one rule, that's all what we have used. Your problem, because we're gonna have a quiz next week on this, right? Now we're gonna be, because we only had one quiz this semester, we didn't have any quizzes. So maybe, yeah, we're gonna have 1 or 2, but we're gonna have quiz next week on this part. So try to pay attention a little bit. So we're gonna have this rule, you're gonna use it. I'm gonna give you a system like this. All what you're gonna do, solve the truss with the original load, remove the original load, put 1 unit force in the direction of the displacement that I'm asking for, and then solve this truss, and then substitute in this rule. That's it.
So if you have like more than two loads apply on the system.
Doesn't matter. You are gonna solve the truss if you have 10 loads. Like I remember when I in a structure analysis, like you can have a truss like this, and you can have a load here, load here, load here. You solve this entire truss for this load, and then you are gonna have forces in all the members. But definitely I'm not gonna do this in a quiz. Maybe in the homework you're gonna have trusses like this.
So the virtual load will be applied on all of those loads?
No, the virtual load is applied at the displacement that I'm looking for. Like I'm gonna ask you to find the displacement here. So you're gonna put 1 ton here to find delta Y. If I ask for the displacement here, you're gonna put 1 ton here and then multiply. But you're gonna find the internal forces induced in the entire truss from this load.
So the other load is still the same, but
Hmm?
the other load will be the same.
Yeah, original loads, we don't touch them.
Okay. And then we switch the one we asking for.
Yeah, like, as I said, step number one, there's no virtual thing. Solve your trusses, and I'm gonna give you determinant trust that you can solve, not a trust that you can solve. So you will be able to solve the trust system that I give you to find the internal forces, but I'm not looking for internal forces, I'm looking for deformation. In basic structure analysis, you didn't find deformation, you only get reactions and tension or compression. You never have been asked for a deformation at a specific point. What we are looking for is the deformation. So you will solve the truss using the basic principles that you have. Once you solve the truss, then you do a virtual work method. You clear all the loads, apply 1 unit load at the location that I'm asked for deformation at. Like if I'm asked here, you put a unit load in the Y direction. If I'm asked for the X movement at this point, you put unit load, then solve the truss, and then make your table and you're gonna make your table like the way that I told you. I'm not sure if I have it here. And then at the end, you can sum all the loads to get this value. Because this is only one value, but this you have lots of members, all right? I think it's as simple as if I'm gonna study at home, I'm gonna understand the concept. Once I understand it, I like try to refresh my memory and I focus only on this rule. Know what does each one mean, and then I solve problems, all right? You guys have the textbooks that, I put the textbook in the syllabus, but maybe because I give you guys notes to might not, but in the textbook you will find, I believe in the second textbook, maybe I put the name again. It's not the Ismaili, it's another one, but I might give the names again to double check, and you'll find lots of problems on this stuff, okay? All right, see you guys next time. We're gonna